Hi everybody, and welcome to Unit 8. And Unit 8 is going to focus on solutions. All right, solutions are mixtures. Okay, and they are what are known as homogeneous mixtures, which means that we cannot visibly see the different parts in them. All right, all solutions, however, are made up of two parts, and that is the solute, all right, or what is being dissolved, and the solvent. Okay, what is doing the dissolving? Now, how do things actually dissolve? Well, we're going to be focused on how things dissolve in water. All right, water's known as the universal solvent. Well, that's not exactly true. It doesn't dissolve everything. We certainly know that, but it dissolves a lot. And a lot of the chemistry that we talk about is in water solutions, is in aqueous solutions. All right, so remember from last unit, water is a polar molecule. All right, and it looks something like this. Remember, with its bent shape, and the oxygen has a partial negative end, and the hydrogen is your partial positive end. All right, because of this polarity, because of these dipoles, water typically can dissolve, all right, other polar substances, so other polar molecules. And when it does that, we say that the process is dissolving. Okay. It can also dissolve most ionic compounds. Now remember back, water can't dissolve all of them. Remember your solubility rules that we talked about. But most ionic compounds will dissolve in water. And when ionic compounds dissolve in water, we say that they dissociate. All right, so let's talk about what the difference is between dissolving and dissociating. Dissolving means that one molecule is going to break away from another molecule, but the molecule holds on to its structure. All right, whereas dissociating with ionic compounds, it means that it's going to break up into its individual parts. So let's take a look at what dissociating actually means. Okay, all right. Water molecules, okay, are going to surround the solute particle. If the solute is more attracted to the water than it is to itself, solvation occurs. So let's talk about what this is going to look like. Let's say we had table salt, sodium chloride. All right, remember sodium chloride is made of a sodium ion and a chloride ion, and they are attracted to each other. But when water comes around, what's going to happen is the hydrogen side is going to, the hydrogen side is going to come near, right? Because that's the partial positive side, is going to be attracted to that chloride, and your oxygen end of water with the partial negative is going to be attracted to that sodium. And those molecules are actually going to be able to pull the sodium and chloride together. All right, this process is called solvation. But when water is your solvent, we call it hydration. All right, so that's with water as the solvent. Okay, great. So hydration is a type of solvation. Okay. When your solute is an ionic compound, like it was with our sodium chloride, what we get is what's known as an electrolyte. And you've probably heard the term electrolyte, certainly with sports drinks. That's where we hear about it all the time. An electrolyte is any compound that when dissolved in water will conduct electricity. And these are your ionic compounds, all right? Your soluble ionic compounds. Okay. Electrolytes are very important to living things. Okay. We get most of our electrolytes that we need, or almost all of them really, from a healthy diet. But that's also where those sports drinks and things like that do get the idea that you need them, is because they are really important. All right. So we can also certainly have solutions where water is not the solvent. Okay. If it is another polar molecule like water, the process is going to be very similar. But you can also have a situation where you have a non-polar solvent. So when a non-polar substance comes in contact with another non-polar molecule, you can also make a solution. How does this happen? Well, those molecules, remember, only have those weak London dispersion forces working. So they don't have any strong attraction to themselves. So there's no strong attraction. All right. Therefore, okay, so no strong attraction to themselves. Therefore, they will mix with other nonpolar molecules. All right. Now, if you try to mix a nonpolar substance, something like oil, with a polar substance, something like water, and you guys have done this before, I'm sure, you'll see they don't mix. And that is actually because of the water. It's not because of the oil. The oil doesn't really care who it's next to, but the water does. The water has those partial positive and negative ends, so it wants to be near things that have those charges. So the water is actually holding on to itself, and the oil just ends up getting separated out. This is where we get the term like dissolves like. All right, if you're polar, you can dissolve something else that is polar or has a charge like an ionic compound. If you're nonpolar, you're going to have the ability to mix with or make a solution or dissolve another nonpolar substance. Okay, great. All right, so with solutions, this is a really fun unit because we get to go back and talk about the mole and deal with stoichiometry and all sorts of good things, because we want to be able to quantitatively describe and then deal with mathematically, all right, our solutions. So a little reminder, when we talk about solutions, remember they're made of two parts: the solute, which is the substance being dissolved, and the solvent, which is the substance that's doing the dissolving. Most common is water, and for the vast majority of our problems, our solvent will be water. All right. So one way that chemists use, and the most common way that chemists use to describe a solution quantitatively, is through what is known as molarity. Molarity gets a capital M as its abbreviation. All right. And what molarity is your moles of solute over your liters of total solution. So just a little bit of a reminder here, a decimeter cubed is the same as a liter. All right. So 1 decimeter cubed is the same as 1 liter. And also 1 centimeter cubed is the same as 1 milliliter. You really want to have this memorized, okay, because we will be using these conversions quite a bit. So please remember, molarity, which gets the abbreviation capital M, not a lowercase, capital M, is moles of solute over decimeters cubed, or liters, because they mean the same thing, of solution. Okay, so we're going to be going over, all right, several different types of molarity problems. The first is just the most straightforward, and that is simply finding molarity. So these questions are going to read, what is the molarity of? All right, so in this case, you just need to remember what molarity stands for. What is the molarity of a solution with 5.6 moles of potassium hydroxide in 250 milliliters of solution? Well, remember, molarity is moles of solute over liters of solution. You have your moles of your solute, okay? You have a volume of your solution. It's not in liters, but we can convert. So I'm going to take 5.6 moles, all right? And it doesn't matter that it's of KOH because we already have it in moles. And I'm going to divide that by 0.25 because 250 milliliters is the same as 0.25 liters. All right, when I divide that out, I get 22.4, and that's in moles over liters, but instead of that, we always use a capital M. So we use that capital M as an abbreviation, but please realize that that capital M means moles over liters. All right, so let's look at question number 2. All right, so in question number 2, what is the molarity of a solution with 22.4 grams of copper 2 sulfate in 2,500 milliliters of solution? All right, well, in this case, I'm giving you grams. Remember, you need them in terms of moles. Well, we can easily do that. We've been doing this for a while. So I have 22.4 grams of copper 2 sulfate. Still need to be able to write formulas. That's never going to go away. All right, in 1 mole of copper 2 sulfate, my molar mass from the periodic table is 159.6 grams. Okay, I'm going to stop here. I get about 0.14 moles. All right, that's great. So I have my moles in 2,500 milliliters. Well, that's 2.5 liters of solution. Okay, so I'm going to divide those out and I get a molarity of 0.056 molar. Okay, great. All right, so that is our first type of molarity problem, just simply finding molarity. Molarity can also be used within a problem. All right, and this is when molarity is going to be used as a conversion factor. Anytime you need to go from liters to moles or moles to liters. So what this means is when you look at the numbers that I give you in the problem, do not start with molarity. Always start with an amount. All right, so let me be clear. When I talk about an amount, it means something I can directly measure. All right, so that's either going to be a mass, which I'd measure directly on a balance, or a volume, which I'd use a graduated cylinder or another container like that. Molarity, on the other hand, is a description. It's telling you the concentration. It's not telling you how much of it you have. All right, so let's go on ahead and take a look at an example. How many grams of solute are in 25 milliliters of a 1.5 molar solution of calcium chloride? All right, so what am I looking for? How many grams? Okay, so I'm looking for grams. My solution is calcium chloride. That's my solute. So Cl2. What am I going to start with? I'm going to start with my amount. My amount is 25 milliliters. Okay, remember molarity, not an amount, it's a concentration. So I'm going to start with my 25 mils. Now I know that 25 mils, I'm going to need to use it with molarity. So I'm not going to use it as mils, I'm going to use it as liters. So 0.025 liters, because that's what 25 milliliters is. I'm now going to use my molarity as the conversion factor from liters to moles, because 1.5 big M is the same thing as 1.5 moles over 1 liter. So that's what I'm going to use. 1.5 moles of calcium chloride per 1 liter of solution. All right, great. Well, I'm now at moles of calcium chloride. I want to get to grams. We've done this a bunch before. In 1 mole of calcium chloride, I'm going to look at the periodic table to find my molar mass. And that molar mass is 111.1. All right. I am then going to multiply everything on the top, divide it by the bottom, and your answer is about 4.2 grams. All right, go on ahead and pause the video here and try B on your own. Okay, so now let's take a look at letter B. What volume, so in this time volume, I'm going to end in liters, of a 2.4 molar solution will contain 5 grams of sodium chloride. So where am I going to start? I'm going to start with my 5 grams of sodium chloride. So 5.0 grams of NaCl. All right, I know I need to get to moles. You always need to get to moles. 1 mole of sodium chloride has a molar mass of 58.5 grams. Okay, all right, now I am going to use my molarity, my 2.4 capital M, all right, as a conversion factor. Remember, 2.4 with that big M, it means 2.4 moles over 1 liter. I can also flip that upside down, and that's what I'm going to do here. For every 1 liter, I have 2.4 moles of sodium chloride. All right, I'm going to multiply everything on the top, divide it by the product of the bottom, and you should get as your final answer 0.036 liters. Okay. All right, to do our third type of problem, it is making a solution, and I'm going to take you into the lab to take a look at that right now. Hi everybody, and welcome to my lab / kitchen. I just wanted to show you the two kind of basic and fundamental ways of making an aqueous solution. All right, the first is when we take a soluble solid, this is some copper 2 sulfate here, and we mass a very specific amount, and we're going to show you how to do that in your calculations in a minute. All right, you're then going to take this solid, the specific amount of this solid, and then you're going to carefully add it to some type of flask, or in my case, I have a graduated cylinder here. So I'm going to be very careful, make sure I get all of that in there. Ooh, sorry, there we go. All right. You will then, okay, for this example, let's say I want to make 100 milliliters of this. I am then going to add what I say is enough water to get me to 100 milliliters. Now, why do I say enough? I say enough because, look, that copper 2 sulfate actually takes up some volume itself. I don't know what that volume is. I don't need to worry about that, all right? Because I know if I just fill this up, all right, till I get to that 100 mark, hopefully you can see that okay, there we go. All right, I'm just gonna slowly fill this up. This is tough to do while filming. All right, there we go. And you can see right there. All right, now it might have a little bit of a hard time dissolving in here. Usually you would use what's called a volumetric flask. Okay, all right, and I'm gonna fill this up till I get to that 100 mark. Okay, and I slow down right at the end, and then there we go. So we have the proper volume. If I give this time, this will all dissolve in that water because actually it is very soluble. It's just taking a minute. All right, and that is how you would make a solution if you were starting with your solid solute. All right, so our third type of molarity problem is where you are describing how to make a solution. Now, as you just saw when I was working in the lab, the first way to make a solution is when you are dealing with a solid. All right, so to make a solution with a solid, you must find the mass of the solid to use. That's going to be the first thing that you do. All right, and then dissolve that solid in enough water to make the final volume that you need. All right, so let's take a look at what this problem is going to look like. All right, describe the preparation of 250 mils of a 4 molar cobalt 2 chlorides, and it would say solution. We just say it like that, solution. All right, so step 1, you're going to find the mass of the solute needed. This is a factor label problem, just like we just did using molarity as a conversion. All right, so you're going to start with your amount, which is 0.25 liters. All right, because remember 250 milliliters is 0.25 liters. I want to end up with grams of cobalt 2 chloride because that's what I'm going to mass on the balance. So 0.25 liters. I'm then going to use my molarity, 4 molar, to go to moles. So 4 moles of cobalt 2 chloride for every 1 liter. Remember, that's what 4 capital M means. I'm then going to go from moles to grams of cobalt 2 chloride. Molar mass of CoCl2 is 129.9. I'm going to multiply and then divide by the product of the denominator. And 0.25 times 4, all right, gives you 1. So your answer ends up being 129.9 grams. Now, this is not your final answer. Your final answer is a description, all right? Because remember, up here I asked you to describe. So here I would write that I'm going to dissolve 129.9 grams of CoCl2 in enough. Remember, when I was using that graduated cylinder, I poured the water up until it was the volume that I needed, into enough water to make 250 milliliters of solution. Or you certainly could have written here 0.25 liters of solution. Okay? All right, going ahead and try our next practice problem. You can pause the video and describe how you would make 55 decimeters cubed of a 0.5 molar sodium hydroxide solution. All right, great. So let's get started. So again, I am starting with my volume, 55. Remember, a decimeter cubed is the same thing as a liter, so I'll just write it as liters. It doesn't matter. And I'm going to want to get to grams of sodium hydroxide, which is my solute. I'm going to use molarity as my conversion. I have 0.5 moles of NaOH per 1 liter. And then in 1 mole of NaOH, my molar mass is 40.0 grams. All right. And when you solve for this, you get about 1,100 grams of sodium hydroxide. But remember, I asked you to describe. So I would dissolve 1,100 grams of NaOH in enough water to make 55 liters or decimeters cubed of solution. This would be your final answer. Okay, great. All right, I'm going to take you back to the lab to show you our other way of making a solution. All right, so we've waited a couple of minutes and I stirred it up a bit, and now you can see that we have our really pretty solution of copper 2 sulfate. Copper compounds make really the prettiest colors, and you can see this is a really pretty blue-green. All right, and let's say this is our 1 molar solution. Okay. Another way that we make solutions is from other solutions, and we call these dilution problems. All right, where we take a solution that has a higher concentration. All right, we take a small amount out and we add water to make a more dilute solution. So we're just going to take this and pour it into a beaker so we can hold on to this. All right. And what's nice about dilution problems, and what everybody likes about them, is they follow this nice, simple little equation. We'll go over this when we go over your notes problems as well. All right. MCVC is equal to MDVD. So what does that mean? Well, the molarity of your concentrated, and now remember, our concentrated in our example is this copper 2 sulfate that we made, times the volume of your concentrated is equal to the molarity of your dilute times the volume of your dilute. All right, so your job is going to be to tell me how to make a solution from this 1 molar, okay, 1 molar solution. That's the molarity of my concentrated solution, okay. What I want is a 0.25 molar solution, and I want 100 milliliters of that. Okay. Well, to make that, I need to take out a certain volume of the concentrated solution. So that's what we are going to find. That's what we're going to solve for. All right. So actually, algebraically, this is super easy, right? Because I have a 1 on this side. I'm going to divide each side by 1. Great. 0.25 times 100. Okay. This is going to tell us that the volume that we need to take out is 25 milliliters. All right, so what's that going to look like? Well, I'm going to take my sample here and I'm going to add, try and do this while you guys are watching. There you go. So 25 milliliters, very carefully. All right, so I'm taking 25 mils, there we go, it's pretty good. 25 milliliters of my concentrated solution. Now remember, I want a total volume of 100 milliliters. Well, what does that mean? That means I have 25 in here. I want a total of 100. I need to add 75 mils to that. All right, so here we go. I just leave it in my graduated cylinder. I just pour it in there. Okay, and what's nice about this solution is you can actually see the color dilutes a bit. All right. There I am. I have 100 mils. Okay. And so now I have my new dilute solution. Okay, great. And if we put them right next to each other, which is nice with a colored solution, we can do that. You can see, all right, I don't know if it's easier. Yeah, it's definitely easier to see on the white there than my countertop. You can see my concentrated solution is darker and my more dilute solution is lighter. Now, obviously, you're not going to be able to see that if the solutions aren't colored, but this is a great example. All right. We're now going to go over these examples in your notes. Okay. All right. All right, great. So you got to see, all right, in the kitchen lab, how to do a dilution. So let's just review what I showed you in the lab. A dilution is making a weaker solution from a stock or highly concentrated solution. We call highly concentrated solutions typically a stock solution. All right. For these problems, these are one of the few where you don't use stoichiometry. You just simply use this nice, simple algebraic equation. All right. MC times VC is equal to MD times VD. All right. Sometimes you'll see this as ones and twos instead of the C's and D's. I think the C's and D's at this point give you an idea as to what's going on. So again, you may see this as MC VC is equal to MD VD, where the capital M is your molarity and the V is your volume. The C stands for your concentrated or stock solution, and the D is your dilute or your new solution. And again, you may see it as this as well, all right, where the ones and twos talk about what we're starting with, and the two is going to be what we're ending with. All right, in your notes, I actually have already typed out an example problem. I want to make 200 mils of a 0.5 molar sodium chloride solution. I have a 5 molar stock solution. How do I make it? Well, again, I'm using my MCVC is equal to MDVD. All right, and the molarity, my first molarity of my concentrated is 5 molar. I want to know what volume of that I need to pour out in order to get a 0.5 molar solution, and I need 200 mils of that. So I just plug those numbers in, and I find that I need 20 mils of my stock solution. So I would take, now again, I asked you to describe. So I would take 20 mils of stock solution and add 180 mils of water. All right, you also could have written enough water here if you wanted to. Okay, let's go on ahead and do this practice. Feel free to pause and try it on your own. All right, how much 1.5 molar hydrochloric acid can I make from 50 mils of a 6.2 molar HCl? So this is still dealing with the dilution problem, so we're going to still use MCVC is equal to MDVD. This one, however, is not talking about making a solution. I just want to know how much solution I could make. So how much 1.5 molar can I make from 50 mils of 6.2 molar? Well, my 6.2 is my concentrated or stock solution. So that's going to go right here. I have 50 mils of that. No need to change this to liters, all right, because the molarity is going to divide out and you'll be left with milliliters, which is totally fine. You don't need to convert that. You can if you want to, though. The concentration of my concentration of the dilute is 1.5 molar. And I want to know how much, what volume, so this is what I'm going to be solving for. All right, the volume of the dilute, how much I can get from that. All right, I'm going to plug all of those numbers in. Your molarity will divide out, and you are left with about 207 milliliters. So you can make 207 milliliters of your new dilute solution from this amount of concentrated solution. Okay, all right, fantastic. Okay, great. So also in today's notes, we are going to do Unit 8 Notes Part 2 because this directly deals with the molarity problems that we were just talking about. And these notes cover what is known as solution stoichiometry. Well, we've already talked about stoichiometry. We love stoichiometry. Remember, those are calculations based on a balanced equation. So step 1 in your solution stoichiometry problem is just like step 1 of any stoichiometry problem, and that is going to be to write your balanced equation. Always, always. All right, great, okay. You then are going to be given a lot of numbers in your problem, so you have to watch out for that. You always want to remember to start with an amount. All right, so do not start with molarity. Remember, molarity is a conversion factor for us. It is not an amount. And then you're going to factor label. So let's go ahead and look at number 1. What mass of silver will be produced when 55 mils of a 2 molar silver nitrate solution reacts with excess zinc? So I have silver nitrate reacting with zinc, and that's going to, and this is a single replacement, so that's going to kick the silver out and give you zinc nitrate. All right, fantastic. I'm going to have to balance, so I need a 2 for my nitrates, 2 for my silver, and I am balanced. What mass of silver? So we are looking for grams of silver here. And I want to start with my amount. So what mass of silver will be produced from 55 mils? All right, well, right there, 55 mils, I'm going to change that to liters because I know that's what I'm going to have to do when dealing with molarity. So 0.055 liters of silver nitrate. We want to start writing what the solution is of because we're going to be dealing with different things now because it is stoichiometry. All right, I'm going to use my molarity to convert from liters to moles. So 2.0 capital M means 2.0 moles of silver nitrate per 1 liter. I need to go from silver nitrate to silver, so I'm going to use a mole to mole ratio. Moles of silver nitrate on the bottom because I want to get rid of them. Moles of silver on the top, and they each have a coefficient of 2, so that's a 2 to 2. Then finally, 1 mole of silver has a molar mass of 107.9 grams. That's from the periodic table. All right, and when you solve for this, you find that you get 11.9 grams of silver. Okay. All right, great. Go on ahead and pause the video and do practice problem number 2 on your own. All right, welcome back. All right, so let's take a look at practice problem number 2. What mass of precipitate will be formed when 35 mils of 1.5 molar silver nitrate reacts with 40 mils of 1.75 molar sodium phosphate? All right, so we have a lot going on in this problem, but it is a stoichiometry problem, so I must start with my balanced equation. And I have silver nitrate reacting with sodium phosphate. All right, great. Double replacement reaction, so that's going to give me silver phosphate plus sodium nitrate. I then need to balance. All right, so I see right away I'm going to have to put a 3 here and then a 3 here, and then I'm good to go. Okay. All right, what mass of precipitate? So you need to use your solubility rules, and you will find that your insoluble compound is your silver phosphate here. Remember, we give that an S. So that's what we're going to be solving for, is that silver phosphate. Will be formed, all right, will be formed when 35 mils of a 1.5 molar solution, so here we go, 0.035 liters, and this is silver nitrate. All right, and I'm going to change those liters to moles using the molarity. 1.5 moles of AgNO3 for 1 liter. I'm then going to mole, so 3 moles of AgNO3 for every 1 mole of silver phosphate. Then I'm going to change to my grams. 1 mole of silver phosphate has a molar mass of 418.7 grams. I got that from the periodic table. And this would give you 7.33 grams of silver phosphate. Be careful. I also give you an amount of the other reactant, which means this is a limiting reactant problem. So now I'm starting with 40 mils, so 0.040 liters of sodium phosphate. That sodium phosphate has its own molarity. It's 1.75 moles of Na3PO4 for 1 liter. Again, that's what that capital M means. All right, I'm now going to do my mole to mole. I have 1 mole of sodium phosphate, all right, for every 1 mole of silver phosphate. And then finally, 418.7 grams per 1 mole. And when you solve for this, you find that that could have given you 29.3 grams of silver phosphate. All right. As we know, for limiting reactant problems, we always choose the smaller amount of product because that means your silver nitrate is going to run out. All right. And there you go. You have answered this question. All right. Have a great one.